I will introduce this gradually, this concept of spontaneous stochasticity, and we will only focus on ordinary differential equations. So I will start with, I recall you what was the problem, then we talk about regularization, implicit limit, and discuss this distinction between unique selection, non-unique selection, or random selection. So in which situation and how they can emerge, and give example. So today is this ordinary, only today we focus only on the ordinary differential equations. So the next time I'll be talking about what we consider as the main applications is the partial differential equations and specific systems. So specific systems which are at the moment mostly related to dynamical systems, but in principle to fluid dynamics, but in principle it can be something more general than fluid dynamics. Okay, so where we are. So let us start. Let us recall very briefly. So what we were discussing, and in which situation this spontaneous stochasticity in principle can appear. So we were talking that we need singularity in differential equations. So this is absolutely necessary because of the Picard theorem. Picard theorem tells that whenever the right-hand side is Lipschitz continuous, there is a unique, there exists a unique solution to the equation. So nothing, no choice can be made. So the already choice is done by the system whenever you have initial condition, even if the system is chaotic and even if there is a exponential divergence of positive Laplace of exponent, exponential growth of uncertainty, still if you exactly know initial condition and the system is exactly determined, deterministically determined, then at any finite time we know what will be the state. So this is a kind of deterministic picture of our life. No? So whenever this singularity appears, this uniqueness may not hold. So here is just a graph again to recall you what is the Lipschitz continuity. Lipschitz continuity means that the difference of the function is bounded by the difference of the arguments multiplied by some general constant k, which is the same for all points. So which means that function always must be within the in the angle. In the green angle here, whatever point of the function you place it. Okay, and again, the singularity means that the function is not differentiable at some point, or it does not satisfy this condition at some point. So which is automatically means it's not differentiable. And as I mentioned, and tomorrow we will see. So in principle, this is not something. Non-differentiability is not something. It's not something peculiar, well, not something impossible in the realistic system, and sometimes it's even opposite. For example, the turbulent motion of the liquid, of the fluid, that what our group is working on, according to Kolmogorov's theory, it is non-differentiable at every point. So at all points, it's not differentiable. It's Holder 1/3 continuous, so it just has 1/3 of the derivative. So it's certainly not Lipschitz continuous. Okay, so but we are not going to consider this kind of system. We'll consider much simpler situations today, which are the systems which has just one point singularity. So we will have system with just one singularity. We place it at the origin. And study what happens. Okay, so the system that I already showed you, and we will sometimes return to it because it's something very, very simple. and at the same time, it's already has some physical motivation. So it's a system where the derivative is proportional to the cubic root of the argument, of the modulus of the argument. And as I said, this is essentially correct phenomenological model of the separation of the two particles in the turbulent flow, for example. So how they separate? So the right-hand side, the function f is singular. It has this shape of the cubic root, and certainly non-Lipschitz. And non-Lipschitz, this property of being non-Lipschitz, it leads to the non-uniqueness of the solution, because whether I have a question. When I share the screen, I have the panel of the, here on the right hand side, I have a panel of the videos and names. Do you see it or not?
No. Anybody can turn this off. So anybody
but
can hide this.
My panel you don't see.
No, we don't see it.
No. So when I because of my panel, when I put cursor here, I'm just moving my panel because it is.
No. We only see your cursor.
I can switch it off and it okay. So
yes. You can switch it off at the top of the video. You can change the view. But anybody can hide this, so you don't have to worry about this.
Anybody has his own panel, right? So
yes, that's right. Yes.
Okay, thanks. So so we have this solution. This is exact solution of this system, which describes. If you start with the initial condition, which is negative, so x here is x vertically time t horizontally. So if you start at negative value, you follow the unique solution because you're on the smooth part of the function until you reach 0. And you reach 0 at finite time. This is important. So 0 is a fixed point of the equation, but since it's non-Lipschitz, you can reach it in finite time, not infinite time like a fixed point in smooth systems. So in finite time, you enter 0. And then from this time on, you have infinitely many options. So you can either just leave it symmetrically, or you can continue. You just can stay at the same point, so you stay at 0, or you can stay at 0 until any moment of time, and at that moment you can make your mind and depart. So you can stay and depart, whatever moment you want. So these are infinitely many solutions, and it's in accordance to the theorem that there is a fact that if there are two solutions, there are infinitely many solutions. So there is such statement. Okay, so this is a system, and so the question, how we will choose the solution after. So let us assume that this is our model, describes our, I don't know, some real life situation, and we know that we're completely happy with this model until it enters 0. But then after 0, we're not happy because we don't know which solution is correct. So we have infinitely many solutions. Model is correct, but which one to choose? So how we choose the solution? And this is something, okay, so we will now start to approach this question, how to choose solution. However, we will do it not with this extremely simple example, but with a simple, though slightly generalized form of the same example. So what we will do, we will consider the right equation in the space of dimension d. So it's a vector. So it's a system of ordinary differential equations. And the right-hand side will have this function R alpha, where R is a norm. So in our previous example, we had R 1/3, right? So that's one third of the modulus. And then it will be multiplied by the function, which is smooth, and it is a smooth function of the direction of the vector. So vector divided by its norm. So of the direction. So it's a smooth function on a sphere. And whenever alpha is smaller than 1, it's non-Lipschitz at the origin. And here there is this example which I already showed. So it's a very specific system. It's everywhere smooth. It's self-similar. So this is a property of the right-hand side of this kind, because it's only depends on the distance through this vector. Yeah, because f of y does not depend on the distance. Y is just the direction. So it is the same field on every sphere, only scaled multiplied by a different prefactor. So it's self-similar. And everywhere it's smooth except at 0. And at 0, we have this situation that whenever any initial condition you take on the left half plane enters 0, and then we have infinitely many solutions, because all the solutions that go to the upper half plane, they start at 0. So we can continue with any solution that goes up. Yeah, so the question how one chooses this solution, and from what kind of arguments you can formulate in order to choose. And this is rather typical situations in application, because in application many equations has singularities, and now usually the philosophy is that whenever you have a singularity which gives you some problem, like non-uniqueness of the solution, usually the ideology that it means that the system or your model is not exactly correct near the singularity. So you kind of forgot some of the properties of the system. So you should improve your system very close to singularity, yeah? And such that the system will be all right. Yeah? And in mathematical language, what does it mean is that we have a singularity just at a point. So what we can do, we can take a small ball of radius nu. So nu will be small. A small ball of radius nu around the origin, and replace our singular vector field by the vector field which is smooth. And it will be designed in such a way that it is smoothly connected also to F, or at least Lipschitz continuously connected to F. So essentially we replace the field inside a small ball by some other field which is smoothly connected. So we take it in such a form, which means that you just choose one G. It's for any nu, it will be connected correctly. No? So it's just because of the scaling of the system. So now the next step is, okay, we changed the field in a small ball. And now the system is now everything is Lipschitz continuous. So there is a unique solution, and we can be happy. But we are kind of unhappy because we have to treat this small neighborhood to understand what happened here. So now what we will do is we take a limit. So the kind of it's the temptation is take a limit of nu goes to 0, which shrinks this region to 0. Oof. And whenever you shrink it to 0, you are back to your original singular system. So if this limit exists, if you can take a limit, so for every finite nu, you have a solution. So now if sending nu to 0 gives you a limit, you can be completely happy because this exactly selects the right solution of your original singular problem. So if this happens, you find a solution. So many questions appear, whether the limit exists, right? What solution it will choose if it exists, and how this solution will depend on the form of the function that you put place here. Maybe another function g you place, it completely gives you a completely different solution, which means that essentially your future is strongly dependent on how you regularize. It's strongly dependent on what happens in the singularity or not. So all this spectrum of different questions that we'll try to answer. So what I can immediately say is that we can prove that you can always have a limit of the solution the strongly convergent limit along some subsequence. So you in general, we don't know if there is a limit when nu goes continuously to 0, but always you can find subsequence of the values of this regularizing constant nu n, discrete subsequence nu n going converging to 0, such that there is a limit. I'm not giving a proof. It's essentially a direct consequence of this equicontinuity argument. So equicontinuity argument, it's something in the spirit of the compactness. So you just proving this property of, you prove the equicontinuity property, which means that in a set of the solutions parameterized by nu, there are always exist convergent subsequences. So this way you find the convergent subsequence, but it certainly does not solve our problem, because it just gives us there are convergent subsequences. There can be many convergent subsequences, and all of them can lead to different limits. So it does not tell you that there is a limit. First of all, it doesn't tell you that there is a continuous limit. Second, it doesn't tell you that there is a unique limit, even with respect to subsequences. So but still there is already some positive information. So there are limits. So in principle, you can take limits, and it already means that whenever you have a very small regularization with some nu, it means that your system is a member of some convergent subsequence. So your solution is can be approximated by some solution of the singular system, by some choice of the solution of the singular system. So the singular system makes sense. Okay, so now let's go back to our system and make some analysis. So the first thing what we do is we have this equation. So we have equation, and this is now, it's not a single system, it's a system parameterized by parameter nu. And we would like to study its solution when nu becomes smaller and smaller and smaller. We know that already we know from previous class that in principle for the open set of initial condition x0, you may have situation when all the solution enter the singularity. So now our question: what happens at times which are after the singularity? So here we assume that TB is the singularity, and we want to see what happens at positive values. So there is a trick. So there is a trick which is the following. So you can find first of all. So this trick is just to give you insight. So you can make a substitution, the ansatz of the solution to the system in the form of the nu, which is small parameter, multiplied by the capital X parameterized by tau nu. So tau nu will be our new time, tau nu, depending on nu. And tau nu will be obtained by the time from the singularity multiplied by nu in the power minus 1 minus alpha. Alpha is smaller than 1, so this is negative power. So by doing this substitution, you reduce this original system to the system of this kind, and this system does not have nu at all. So this is a good part. So this system has no nu, doesn't have a small parameter anymore, and small parameter is only in a relation between the tau and t. So the small parameter which we want to send to 0 is in a relation between tau and t. So essentially what it does is this transformation is just uses the fact that our right-hand side is scale invariant, so it has this scaling structure. We kind of zoom our system such that the ball of radius nu become ball of radius 1. So we zoom the system in such a way that ball of radius nu become ball of radius 1. and we find a solution to this system, and then we scale it back to original variables. And so what you can see is that if you want to find the solution at some given time after the blow up, as nu becoming smaller and smaller, your time tau should become bigger and bigger. So essentially, the solution that we want to understand in the implicit limit is the solution of the system which does not depend on nu, and we're interested in the value of the solution at very large time. So you already see some taste of the attractor in the system, the taste of the attractor and dynamical system. So this already gives you one of the options. So the option one, the kind of trivial option for the choice of your solution, and this trivial option corresponds to the system, to the case when this system, which we rescaled, has an attractor. So whenever the system has an attractor, it means that X capital solution will be bounded. It will be trapped. And then when we recover X original in original time, it's the same as X nu as nu goes to 0, which is the same as limit of nu goes to 0 of the nu by capital X, but capital X is limited, so limit is 0. So this just shows that implicit solution is trivial. And this is exactly would correspond to our simple example when you move until the singularity and you stop at the singularity and continue and stay there. So you continue at 0. So there is a way how so some of the regularization will just choose. So we just showed that some of the regularization will just choose trivial way how to continue our solution. So you end the singularity, and despite there are many solutions, you'll just choose trivial one. So you stay there. And this is it's clear that this situation is robust, because if you slightly change the regularization, this function g inside the ball, the attractors usually they have the property to be robust, so it means that they remain attractors, and this means that you don't need to know this regularization exactly. So even changing regularization, it still will give you the trivial choice of the solution. So the trivial choice is one of the choices which can also be robust. Okay, so this is option one. So now we want to study option two. Option two is when the solution after entering the regularization region will exit the regularization. So this is what we will call expelling regularization. So we assume the regularization is such that after entering, the solution exits and goes away. So the regularization is such that it enters and goes away. And then this analysis is different. And we proceed very similarly to what we did for the blow-up. So we take our field, we split it into the longitudinal component, into the transversal component, and then we make a change of variables. So we take variables which is just longitudinal variable, and then we take logarithm of the transversal variable, then we take logarithm of the longitudinal variable, which means that the distance, log of distance can go from -infinity to +infinity. And also we substitute time from tau to s, which is obtained for some interval. So when we do this trick with this system, we reduce our system, which was regularized, to the system which is now this kind of system they called master-slave equation. So the first is a master equation. So it's a question which only depends on its own variables. So it's a question for y, and y is on a sphere. So it's a smooth dynamical system on a sphere. And then there is a slave equation which only depends on y and gives you z. So this gives you distance from the logarithm. It gives you logarithm of the distance from the singularity. And then by integrating this slave variable, we obtain time s. And we relate time s to the it defines implicitly this time tau of the region. So there is this sequence of steps for the rescaling. I probably should not go too much more details because it becomes too technical. But there are what is important is that there are a sequence of steps how you can rescale the system, so that finally you everything depends on a nicely behaving dynamical system on a compact set. And all the rest, like a distance from the singularity, the time, and so on, they are recovered by integration. And now comes a very important observation, which is make a main distinction of what happens at the pre-blow-up and post-blow-up dynamics. So what happens before coming to the singularity and what happens after coming singularity, being at the singularity. You start. So let's recall this last lecture. So we start with some initial condition, and we start in initial condition. And remember, so we argued, we showed that whenever and we have a system, we have this system, rescaled system, which describes behavior of the pre-blowout dynamics. And this pre-blowout dynamics is given by some attractor of the system, which describes which describes the way how our solution enters to zero, enters to this small regularization range. So the in other words, convergence to attractor in this special system, in this system on a sphere, describes a asymptotic way of the solution before the blow up. Yeah? So essentially the attractor of the system describes the future. So the attractor, this attracting behavior corresponds to the final stage of the pre-blow up dynamics, like the future state of the pre-blow dynamics, just before entering the singularity. So now what happens at the post-blow-up dynamics is completely opposite. So we're described by exactly the same system. So we get exactly the same renormalized system, the master-slave equation, the equation for y and equation for z, and then recovering time. But now the initial state is given by regularization at the past. It gives in the past, and as we shrink this small ball to zero, this past becomes infinite past. So somehow when you do this, when you shrink this regularization, your initial condition, which is this point when the solution comes out from the regularization region, so it becomes a system. No? So this initial condition goes to minus infinity. So it's a situation of the limit when you impose initial condition by regularization, and this initial condition is given at the time s, which is sent to minus infinity as nu goes to zero. So you give your regularization means that you prescribe what is your state at minus infinity for s. And what does it mean? It means that not only initial condition is sent to the past, but also convergence, all the process of the convergence to the attractor is not what you see, but what already happened before. So whatever finite time you consider after blow up, in the limit of nu goes to zero, your initial condition is at minus infinity, and all the convergence to attractor happened at minus infinity. Okay, so this happened in the past. So the UK, and this allows to prove the theorems. This allows to prove the convergence in the theorem. So I won't even go to the proof because they're normally quite technical. But the conclusions are much more transparent. So remember our system, two-dimensional system that we had. It's two-dimensional system, which means that if you draw the reduced equation, this equation for y, this will be a fun equation for on a circle, no? Because the direction on a plane is given by the circle, so this is by the angle, and the system on the dynamical system on a circle, which correspond to this equation, is simple. It's shown here. It has two attracting fixed point and two repelling fixed point. So which means that whatever initial condition you take on the left hand side, you will go to this fixed point. As this fixed point shows you correspond to the solution, this fixed point correspond to this horizontal solution. You see, and the fact that all of them will converge, it means that all initial conditions that you take on the left will eventually become asymptotically get close to this horizontal line. So all the solutions that enter to zero, they asymptotically follow this horizontal line. So this is how they enter. So after the blow up, the solution after the blow up, they are described by this fixed point, which is described by the average of some condition. So we have this condition that so the modulus of average of FR was negative. It's for the pre-blow up, so post-blow up it must be positive. It's just some algebraic condition. And so if we have fixed point with this algebraic condition, what we can prove is that solution which will be chosen irrespectively of the explicit form of the regularization will choose exactly the solution corresponding to this point, which means this horizontal line. So it is given here explicitly. So essentially, what we say that the theorem tells that whatever in this particular example, because there is only one fixed point attractor which correspond to the solution which go away, whatever expelling regularization you put, so the regularization which will not trap the solution but will leave it away. I'm not giving this technical description of what does it mean, but essentially whatever regularization what you put in a small ball of radius nu, which will not trap the solution, and you taking the limit of nu goes to zero, you will always choose this green solution. You cannot exit with respect to any other solution. You only can exit with respect with this green solution. So you are choosing one unique solution out of many, and you see you actually don't you don't even need much information of regularization. You just need to know that regularization will not trap it. Whenever regularization you take, it will lead to this solution. So in some other words, the system already before you regularized it already knew that we will go in this direction. So because there is no other way. Whatever regularization you put, it will expel in this direction. So in a summary, this example has just two options. There are two possible options how it can behave after the blow up. It's not the two possible options, but to say the two robust options. So in principle, you can cook the regularization which will choose some other trajectories as well, but it will be very, very specific regularization. Arbitrarily small deformation of it will just destroy it, and you will go back to this situation that I'm going to tell. And this is a robust choice. There are two robust choices that system can make. Either you stay at singularity or you go along this green line. So nothing else can happen. And this is described by these attractors. No? So this is the situation, and the same situation you would have in our very trivial example. So you can also prove that depending on the regularization, you either can stay at 0 or you can immediately leave along this trajectory. You cannot choose any other path. And this is quite rich information, no? Because this information does not this information about attractors does not actually rely on any properties of regularization. So we just, irrespective of regularization, we know that typically we either stay or go along the specific trajectory. So nothing else can happen unless something is extremely fine-tuned. Okay, so this is this situation, and this is situation which I will tell next time, which correspond to the Burger's equation in partial differential equation. So in Burger's equation, we have blow up, and after blow up, you can formulate different conditions, like a condition of of entropy condition, of viscous regularization condition, and so on, and all of them give you just exactly the same shock wave. It's just exactly the same continuation as a shock wave. And if you change them a little bit, like change the dissipative mechanism, you still get exactly the same shock wave. And this is in spirit very similar to what we have now. And actually, I will show you that there is an attractor which is actually responsible for this shock wave in the Burgers. Just similarly to this very simple ODE case. Okay, one I think nice comment is that this regularization idea already leads to the spontaneous breaking of time symmetry. So this is what physicists, for example, like very much, is that to tell that we have a time error. So that they tell that something in future is different from the past. So I'm not giving you exactly the system, but imagine this kind of equation. This kind of equation with on a plane with this kind of trajectories, and with a singular point here, here in the center. So all of the trajectories from this region, upper region, they enter to 0. So all of them enter infinite time to 0. And then the question, they can exit along the different trajectories, which is any trajectory in the lower part is a trajectory that starts at 0, infinite time. And in principle, the structure of the orbits is completely time reversal, because you can, this vector field is completely symmetric if you change arrow of time together with changing x. So x to minus x, t to minus t, which means that making the central image of this picture plus changing this direction of the arrow gives you the same picture. But now, if you think of the system as a system which is regularized very, very, very close to the origin, and then taking the limit of the regularization shrinking to 0, you should consider this picture, which is a picture corresponding to the rescaled system. And this rescaled system gives you the only one fixed point attractor which corresponds to the future, the post-blow-up solution that may happen with the regularization. Which means that this, in the same way how we did it up to now, we can prove that if you take small regularization and shrink it to 0, generically, so in a robust situation, you instead of this picture, you will have this one. So all the solution from the upper part will enter infinite time to 0, and all of them will exit along the same path straight down. So you see that this means that despite the original system is time reversible, actually the choice which will be given by almost any regularization will be unique, and it will break time reversibility. So you see that this picture obviously is not time reversible. So if you change the arrow of time, it's not even make sense. Okay, so up to now, everything is deterministic. So up to now, we succeeded to choose the solution in the future, but this choice is deterministic. So no probability. So everything in the future is well defined. So how we where the probability can come from? And probability can come from the fact that, in principle, post-blow-up dynamics. So, because all what we discussed so far was about the attractor, which is fixed point. But attractor doesn't have to be fixed point. It can be periodic attractor, it can be chaotic attractor, and so on. And all what we have is the analysis that we constructed for this rescaling is that the pre-blow-up dynamic corresponds to the dynamical system, which those entering to the singular point correspond to infinite time, infinite future. And then regularization just picks some value of these dynamics at very, very large times, and connects it to the some value at very, very, very close to minus infinity times for the post-blow-up dynamics. So we have the same, exactly the same dynamical system describing pre-blow-up and post-blow-up, and there is a connection. So the future point of, far future point of the pre-blow-up dynamics is linked to the far past moment of time for the post-blow-up dynamics. And this is the whole role of the regularization. Regularization make a connection of a future point on pre-blow-up dynamics to the past point of the post-blow-up dynamics. And then by shrinking this ball to zero, it means that it will be infinite future to infinite past. Okay. And so what is important in this picture is that since it's infinite past, it means that also if this point falls into the area of attraction of some basin of attraction of some attractor, that also the convergence to this attractor will happen in the past, which just means that it doesn't matter to which point your regularization have chosen. It only matters in which basin of attraction it was chosen, because it will eventually go to attraction to the attractor, and we will not even know which was the original point. We will only know what was the basin. Yeah, so this is the message. And again, I will skip all the proofs, but so what can be proved in this situation? What can be proved? One situation, interesting situation, is a periodic. So when the attractor of the system is periodic, so remember, so we're told that we are on our rescaled system is on a sphere. And this is example of the system which I already showed last time. So it's example of the system which is on a sphere, and we have a periodic cycle. So the stable periodic cycle on the sphere, and we assume that after the our solution entered in the singularity, which is the origin, our regularization is such that it throws the initial condition to this to that basin of attraction of this cycle. So it's a specific system with specific regularization, and the theorem tells that you can have a limit in of the solution of the regularized system if you take the limit, if you take viscous parameters going to zero along the specific geometric sequence. So if you take nu as exponent with some prefactor multiplied by n plus parameter goes to 0. So n 1 to 3 and so on. So this is a geometric sequence going to 0 as n goes to infinity. Then there is a limit. But this limit is different for different parameters chi. So there are different limits for different subsequences. So we are exactly let me go back. So we're exactly reproducing this this exact result, telling that whenever we regularize and send this parameter to 0, there are subsequences that do converge. There are subsequences that do converge, and in that case we can find these sequences explicitly. So in this case we find So we find subsequences which converge, and we find what are explicitly subsequences which converge. And more than that, we show that this convergence, these subsequences converge to different solutions for different chi. For different parameters, you can converge to different solutions. And this picture below shows that the orbits for different choices that you can obtain in this way. So you enter for same initial condition, you enter the singularity, and then depending on which regularization you choose, so which SIP subsequence, you're choosing one of these spiral curves. So one of the family. So you know the family of the solution which you can choose. And actually, this family does not depend on the regularization. It only depends on the parameter chi. So whatever regularization you put, you always choose this family of the solution. You will go along one of them, this you know. Which one of them depends actually on a small parameter. But at the same time, this set of solution, though it's infinite set of solutions that you can choose, it's still very zero measure subset of all other possibilities. There are much more other possibilities, but we know that only this possibility can be chosen. So this is a situation which is intermediate between spontaneous stochasticity and deterministic continuation. So now continuation is semi-deterministic. So you will go along one of the solutions from a family that you know, and the choice of the solution will depend on the value of your very small parameters that you put. So there are deterministic solutions, and they depend on which nu you choose, which infinitesimal nu you choose. So now we come into finally to the main part. Is the case when attractor on a sphere is chaotic. So what happens if the attractor is chaotic? So now certainly the implicit limit does not exist. It exists along the subsequences, but this doesn't make any sense from the point of view of choice. And whenever the attractor is chaotic, we just simply cannot use deterministic regularization anymore, because it does not give us any meaningful answer. So in order to get meaningful answer, you should put something extra. So extra is a noise. So now our regularization is the following. So we we take in this small ball, instead of considering deterministic field, we put a random field. So we have a deterministic system everywhere around, but in a small ball, we put a random field. So how you put a random field, you can do it in many ways. It can be, for example, the stochastic differential equation, or it can be differential equation, which is deterministic, but depends on the randomly chosen parameters. So it's also give a random realization of the field inside. So what is important is that after your solution, which was deterministic, entered to this very small region, in this small region, it has a random dynamics. So it enters at random point. in certain random point, which is described according to some probability measure. So there is probability measure. So this is exactly how the problem can be formalized. Is that regularization, instead of associating the entering point to exiting point, it associates entering point to some exiting measure, probability measure, with respect to which it will exit. And then what we do is we take this small ball and shrink to zero. We take the small ball where everything non-trivial happens or random happens, and we shrink to zero. And whenever they shrink to zero, the system becomes back deterministic, formally deterministic, like Lorentz wanted. But now we can think about limit. So what system we get in the limit? And the solution in the limit, so how you understand solution in the limit? Already solution for every finite nu is stochastic, right? So because you had a segment of the solution which was stochastic, which means that now your solution at all times after it entered this new region is described by measure. So every time the solution is a measure, probability measure, which gives you at which point with which probability you can find your solution at that specific time. So now we take a nu going to zero, and the question, what will be the limit of this measure? Okay. So now, if the attractor was a fixed point, the measure will collapse to the Dirac measure, so it will essentially choose the deterministic solution, just the same solution that we was before, considered before, but it's not the case if the attractor is random. So now what you have is that this is schematic. So this is the first gray spot is distribution. Imagine that this is a distribution given by your regularization. So regularization is random. So it gives you some spot in your space which correspond to the possible solutions on this sphere. But then as you evolve the system, these spots start to go to the attractor, and at large times it completely converges to the attractor. So this, independently of what or what was the original measure, you go finally to the measure which describes the behavior on the attractor. So usually it's called SRB measure or physical measure. So finally you will have distribution, or your possible solution will be distributed on the attractor. And what is important is, as we shrink to this new ball to zero, all this region that we correspond to the convergence, it goes to the far past, and at each fixed time, your system, your angular part of the system, which correspond to the just probability distribution of the attractor. So this is picture. I will show you the movie, so you can probably feel it better. But what is important is this kind of limit gives you the concrete probability distribution at every finite time. So at every finite time, your system is at some point in the space with certain probability distribution, and this probability distribution is uniquely given by the measure of the attractor. So it does not depend on the regularization again. So regularization doesn't matter. Regularization is just a way how to recover this information, because the attractor is a property of the original singular system. So original singular system already know how it will distribute probabilities. And we can prove it rigorously, and we have theorems in the case of two attractors, for hyperbolic attractors, and for some subclass of geometric Lorentz attractor that includes Lorentz attractor itself. And again, I will not give you the exact statement, but statement is the following. So whenever you have a regularization which is random, and which maps inside that very small ball of radius nu, it maps original point to some continuously, absolutely continuous probability measure, which is inside the basin of this chaotic attractor. Then the solution at post blow-up time can be found explicitly. So it's exactly the SRB measure of our rescaled system. And then we put some scaling operator to this measure, and we find the solution for the positive time and for the time after blow-up. So what does it mean? That considering this system, which was singular and which was probabilistically regularized in a small ball of nu zero, then sending to nu zero, we have explicit solution, which is deterministic before the singularity and probabilistic after the singularity. And the SRB measure of our attractor gives you assigns probabilities to every possible solution to which you go. So first of all, it shows along which solution you can go and with which probability. So there is a probability measure which describes what happens. And certainly it's easier to see than to read. No, so this is a model. This is a specific system of equations in 4 dimensions. So there is a x is x1, x2, x3, x4. It has just singularity at 0, and then it was it has this exactly the structure that's R alpha by f of y. So we found this we constructed the system of 4 equations explicitly with singularity 0, and it will have all. It has this property. It has these properties of the theorem. So it will have a fixed point attractor corresponding to the pre-blow-up dynamics and chaotic attractor for the post-blow-up dynamics. And this chaotic attractor is exactly cooked, designed using Lorentz attractors. So somehow. So there is a fixed point in pre-blow-up and chaotic post-blow-up, and you will see what happens. So there is a very small regularization which we also incorporate, and this regularization will be in a ball of size 10⁻⁵, and we will see how the solution will behave. So what happens is that we start with some initial condition, and we will track, I think it's 10 or 100,000 different solutions. 100,000 solutions we will track along them. So all of them are start at the same point. So they follow the same trajectory because it's unique solution until it hits the singularity. So important that it's 4-dimensional space. So it's just x1, x2, and there are 2 more dimensions, so which we just don't show. So we will see the solutions which hit singularity and in a very 10⁻⁵ radius neighborhood, we have a random regularization, and then we will see how what solution will be chosen. You see, they all go together. There are a lot of solutions together. The group of many solutions, they go together. So they slightly decelerate when they come close to the singularity, but they will still enter singularity in finite time. So you see the time is up to the blow up is computed. So now at time 0, it enters near the time 0, it enters the regularization region, and very fast it exits. But you see that so these green points, how many of them? Let's see. So there are 1, 2, 3, 4, 5, 6, or maybe 7 green points. So they show specific 7, 6, or 7. I think this should be 7 points. 7 different specific solutions, and the shaded region is a probability density function which is obtained from 100,000 solutions. So it just shows you where it's darker, it's higher probability for the solution to be found there. When it's lighter, it's lower probability. And you see that, so if you follow one single solution, you're any point there. So if you follow any single solution, you never can predict where you are. So you can be at any point on that tractor. But if you follow many solutions, you can recover. You can see what is the probability distribution where you can be, and you already can kind of guess. So this is the shape of the Lorentz tractor. So essentially, you can even having the probability distribution of Lorentz tractor, we can find what is the probability distribution for at every single time of the system. And this probability distribution does not depend how you regularize. So it's already probability distribution which was known to the original system. So original system with the singularity already knew that after it will pass the singularity, there will be probabilistic behavior. And this probabilistic behavior will have a very specific probability distribution. Oops. We have to start again. Let's see it again. So we start with some value. Approach the singularity. So it's coming closer. It's deaccelerate because it's power law. But eventually it comes to singularity. Then we have a very, very small region where it is regularized. And it's already enough to completely randomize the future, despite the dynamics. You see, the dynamics already is completely deterministic. It's just that it was only random at a very, very small initial, very small neighborhood of the singularity. So after it exits the point, it's completely deterministic. But it's now deterministic evolution of the measure rather than of the specific solution. So this is what happens. Okay, so what are the key properties of the key property of the solution is that blow-up solutions are selected from infinite subset of solutions. So it's not one or two solutions can be selected. Infinitely many of them can be selected. Does not necessarily the regularization does not necessarily select one single solution like a shock. There are situations where it can select infinitely many, and the choice of the solution can be probabilistic, is defined by the SRB measure. And what's even more, that this choice can be insensitive to the details how you regularize. At the same time, you must take into account noise in this regularization. But what is the noise? What's the specific form of the noise doesn't matter. It will choose exactly the same probability distribution. If you want to have uniqueness, concept of uniqueness for your solution, it's only unique in the terms of a measure. The measure, probability measure, is unique, but specific regularization is not. So in that sense, there is a spontaneously, the system spontaneously becomes probabilistic. So it is deterministic until blow up, and after blow up, we will have a unique continuation as a probabilistic measure. So only in probabilistic way. So I think that's it for today. It was quite technical. So day after tomorrow, I will show you partial differential equation where this phenomenon happens. So in partial differential equation, we have way more limited understanding of how this happens. So you can see a lot of information by analogy between the ordinary differential equation where it can be proved and partial differential equation where it can be analyzed, and you can recover many similarities between what we see here in ordinary differential equation and what we see in partial differential equations. but certainly you can see the same consequences. The same consequences that the system solution is deterministic until a certain moment. At that moment, the system loses Lipschitz continuity, so you get blow up, and you in fact can extend the solution after blow up using some regularization procedure. But this extension chooses, but the extension is now become random. So the future, the destiny of the system is now cannot be is not deterministically predicted. But what we know is that we can know the distribution. The distribution seems to be unique. Yeah, it seems to be unique. So this probability distribution seems to be unique. And we will also show not only differential equation, but specific phenomena where it may occur. And one of the phenomena is where we verified it numerically, where it can happen is Kelvin-Helmholtz instability. And this is instability in fluids. And I got the picture of the instability so that you will believe this instability exists from one of our postdoctoral fellows from our Simon Talabar. He sent me a picture that he took some months ago from, I think it's from Vista Chinesa, Mesa do Imperador, here in Rio. And this is instability that you can see along this line. And this instability, you see that there are these vortices that start to appear, and this is instability which occurs when the one layer of air flows with a different speed on top of another layer of air, and this instability creates the vortices, which you can see that here created, and they later develop in they start to mix and develop in a rather unstable way. And this is one of the roots that lead to spontaneous stochasticity. So this is one of the example where spontaneous stochasticity can be applied. So it's at later stages of these dynamics are become unpredictable. Okay, so I think I finish for today. And for the day after tomorrow, I promise partial differential equations and realistic systems. So this will be, and open questions. There will be a huge amount of open questions, which are extremely interesting for analysis. I think they're extremely interesting for analysis because these are all dynamical phenomena which has little analog or not clear analog in dynamical systems. So there will be many phenomena which occur in the partial differential equations, but do not occur in ordinary differential equations in a simple way. At least we don't know how they occur in neither one. At the same time, you can study them numerically and see what happens and try to maybe create a theory, the analysis. Okay, so thank you very much. Yeah, so.